All right, so I'm going to go over setting up sinusoidal signals and then measuring them. So I'm in the signal generator tab right here. You can see that off to the left there, and then all the different options here for our types of signals. We've been using our DC, which was our constant. Now we're going to use the waveforms, various waveforms. Right now we're going to use sinusoidal signals. You can see there's square wave, which we'll use later. Maybe we'll use triangle wave in the class. So there's a couple of signals that we're going to work with. And then in our settings for our sinusoidal signals, we need to set both the amplitude and the frequency. For our current situation, the offset's always going to be 0 and the phase is going to be 0. So there's our source signal with a 0 phase, and then an amplitude is indicated in the lab. I've set the amplitude here to 2 volts, and I've set the frequency to 159 hertz. So one thing to remember is that when we do our analysis on our circuits with our impedances, it uses radial frequency or omega. And so 159 hertz is 1000 radians per second. We've seen that number before, so I just wanted to remind you. So this is set for 2 volts at 1000 radians per second or 159 hertz. And then we need to start this signal. So to remember, in the upper right corner, we hit run. And so now I'm outputting that 2 volt signal, 159 hertz or 1000 radians per second. Now we need to make our measurements. So the oscilloscope is used to make our measurements. And right now, nothing's being measured. So down in the lower left here, you saw this in the voltmeter, we have a channel 1 and a channel 2. We're going to use both channel 1 and channel 2. So it indicates in the lab that we want to measure our input signal, which is the W1 signal, and then our output signal. In this case, our output could be the voltage across the capacitor or the voltage across the resistor, or whatever the case may be. So you want to make sure both of these are checked on. I just checked them both off. You can see them, the traces disappearing on the oscilloscope window there. I turn them back on, and the orange line and the blue line show back up. Right now, the oscilloscope is not running, so I need to click on channel 1 and set things as appropriate. So I'm going to hit run here. And there's the signal, and this is actually already set up. There's a couple quirky things here. I like my position to be 0. Occasionally, if you mess around with it, it drifts off. So that just kind of centers the signal. There's a little bit of noise in the signal, you can see, because my circuit has a couple issues in the way it's set up, but it's mostly a clean signal. One of the things you need to do is set the time base. So I've already done this, and the volts per div. So if we set this incorrectly, we'll get very difficult to see signals. So if I set that to 100, you can see that it's just not something you can visually see. We want our time base to be close to our period. And so at 159 hertz, the period is 1 over 159. And you can go through the math there and figure out what that is. So remember, the relationship between period and frequency is an inverse relationship. T equals 1 over F. So we want to see a couple, 3 waveforms. We see pretty clearly 2 waveforms here, a little bit more than 2, or periods, I should say. So this is part of your exercise, is set the time base accordingly. And likewise, we want to set the voltage level accordingly. So right now, once again, it's set correctly, but if I were to do something, change it to 10 volts, then we see orange just disappears, and we want to be able to see our signals. So we want to, again, set this correctly. So I can put it on 0.5, which was 500 millivolts, is what we had just a second ago, and we get a nice clear signal. That's setting the orange. In order to select that, then we click this here. This brings up this radio button down in the lower left, brings up our settings for our oscilloscope channels. And then you need to do the same thing for channel 2. In this case, I want this to be the same volts per div, so we're going to make that 0.5. I like to see the same scale. The time base is the same as well, so we want those to be kind of roughly the same in order to see them. We may want to adjust our volts per div if we have a hard time seeing the signal, and that's something you can work with going forward. So there's our two signals. In this case, I'm measuring an RC circuit. Orange is my W1 signal, and blue is the capacitor voltage. So the final thing we're going to work with when making measurements here is we're going to use cursors. So down here on the lower right, you can see there's a cursor radio button. So I'm going to bring up cursors, and then we want to bring up the control tab. So off to the right here, on the right side of cursors, there's the little radio button that brings up the controls for the cursors. You can see it says cursors there at the upper right. Most likely both your cursors are off. So if we want to measure amplitudes, we can turn the cursor on, and then here's a control. Oops, not that guy. That was horizontal, sorry. Amplitude would be vertical. The gray bars here give us the amplitude, and we can adjust them so that they're at the peak voltage, and then the minimum peak, the most negative peak, and there's our peak to peak voltage. The amplitude of a signal is 1/2 that, so that should be twice the amplitude. And you do want to measure from peak to peak as opposed to just offset from the origin, because there are some DC noise offsets here. Excuse me, sorry about that. So there we can get the amplitude using vertical cursors. We can turn those off if we want, or you can leave them on. The values are up here on the upper left of our oscilloscope window. So we can turn those cursors off. Oops. And then turn on horizontal cursors. And if we line these up with the peaks, we can get, excuse me, phase shift in terms of time. So again, now that these are horizontal cursors, you can see delta T is given to us as 750 microseconds right there. Cursor 1 minus cursor 2. That's the difference. And that's what we're interested in. So phase shift is visible in terms of a change in time. It's the shift of the sinusoid, and because the x-axis for an oscilloscope is a time axis, then phase shift actually, from a measurement point of view, is a delta T, or a change in time. We'll have a separate video on how to convert that delta T to degrees or radians or whatever you prefer to use. But when we make measurements, the phase is observed in delta T, and what I usually do is go from peak to peak. And so I line up one of my cursors with one peak and another cursor with another peak, and then find the difference between those, and that's what a phase shift is. We'll stop that video.